Hello all, this is Milt Olson with Maintenance Technology Systems. On this little video we're going to do an overview of how our Vbox5 32 channel data acquisition device works and functions. So this is what our data acquisition screen looks like, and I'll show you how it actually gets there. When we first start up the program, it defaults to this particular setup. This is our analysis screen, our basic analysis screen. So when we're going to acquire data, we select this option here, gives us a large window where our data is going to be displayed. And we've got several things we need to do here. So let's work across the top. So in this file name box, it becomes the root of our file name. And so we'll just call this, say, video 1 test data. Okay. And that's what it's going to be. The default setup, and we'll go ahead and change this. We can access here. It shows it how it's worked. We ask if we got attack data or not. We can recall data, and we can filter the data. And this filter works as a high pass filter, low pass filter, or band pass filter, depending on where we set these frequency ranges for the filter. So just keep that in mind and play with that as you go forward. Starting down the other column, we have our channel setup, and we'll go into that in just a moment. We're ready to acquire data. This is where we start. Choose to show the waveform of the FFT. The data acquisition mode can be either a continuous or a triggered mode. Continuous actually gives us continuous uninterrupted data for the duration of the data set. And then it takes a new data set, and the next data set starts exactly where the other one ends. Have a trigger set. Frequency range, I think we'll drop this to 1,000 hertz for now. The rest of this just shows information as it's acquiring data. So we'll see that here in just a few minutes. In the channel setup area, we'll just give you a quick picture there. If we click that, brings up the default setups that we currently have. And all of these are changeable, addable. We can add up to 32 channels, and we'll have actually a video just about that one on how to do setups. So just wanted to show that to you. Notice that these channel labels match the channel labels here in this drop-down list. And so we'll go back there, and there's those same channel labels. So we'll just leave it like that. We'll go ahead and acquire some data here and talk about how this data acquisition works. So this is a data recording device, and as you can see, it's essentially a 1-second window is what it attempts to do. We've got our channel 1 is at the top through channel 16 here at the bottom. The reason channel 1 and channel 16 look different is in channel 1 we actually have an accelerometer attached. I'm just attaching that with my finger. On channel 16 down here at the bottom, we actually set that up, if you noticed in our setups, to be our tachometer, and so it's looking at a voltage signal and waiting for that to come through. The rest of these are just open circuit sort of data there. So go back over here now. This tells us that we're acquiring approximately 2,000 data points per second, give or take, so that our frequency content is 1,000 hertz. So that's the actual numbers, and our calculated Fmax in our spectrum when we get to that from this, it will be 1,000 hertz. Note that the shaft speed is showing up as 0. Notice that we have a countdown timer here. Started out about 1520, and it's counting down. When it gets to 0, it will write this data set to memory, to the hard drive. Notice that this is counting up, tells us we've got 82 seconds, 83 seconds. We don't have to specify this on the front end. We can simply say, oh, I wanted 100 seconds of data. The event I wanted to watch has happened, so on and so forth. And so when this gets up to 100, I'll go ahead and hit stop. And it's going to say, where do you want to store this? And I can go here to my C drive, scroll down, let's put it in our MTS folder, let's call it data, and I could make a new folder here if I wanted, or I could just simply go to a default directory, which this TWF data is, Let's go ahead and make a new folder, call it video test folder. Whoops, two fat fingers here. Oh, there we go. Click off of that. Make sure it's highlighted, hit OK, and this should be our data set that is there now. Now, once I've acquired a data set, I can do a number of things. One, I can look at that. Notice that this is our transducer settling in here. That number's pretty big compared to what I'd like it to be. Let's make it 15 so it matches. It auto scales initially, but we can simply double click, change those numbers to whatever we want them to be. Also notice here that this is where I was tapping the vibration transducer with my finger. Notice that we've got a couple of different cursors we can move around. Let's turn this scaling off here. And as you can see, as we get in here, there's some noise that comes up in our spectrum. So the basic game plan is here we've got 100 seconds worth of data. It's all continuous data. Phase relationship between all the channels, all of those kinds of things are intact. And note that as we move the cursor back and forth, we get a spectrum where the cursor is at. Notice also that I've got a family of cursors here. I'm trying to pull that apart, but it's not working too well. There we go. That these cursors respond to where the cursor is in the spectrum. And note that the stuff over at the right-hand side updates that process. If I want to look at one of these other channels, I would just simply select that. Notice we've pretty much got noise again here. I'm going to go back and reselect this first one. It's got a little bit more interesting data in. Notice we have a readout for the cursor values over here on the left-hand side. If I move the red cursor, it basically updates on the right-hand side. If we had an RPM signal, it would show that RPM of the cursor, so on and so forth. Note that we can move the cursor, or I can click to a location. I'm going to perhaps make this say 200 hertz. And it spreads that out a little bit. Bring this cursor back there. On the top of that peak, it's notice that it's millimeter units. We can change that to English if we would like. And change this to say 0.2 perhaps is a good number. Yeah, that looks pretty good. So we've got a single cursor, harmonic cursor. Notice that we can move these and the harmonics go accordingly. Notice our spectrum tends to show the noise around where it's at. I can have this be in acceleration units, displacement units. Of course, displacement units, I have to get some bigger numbers here so we can see it on scale. If I do this as an auto scale, it would have taken care of that. Go back to velocity, it's kind of middle of the road. Change this back to 0.2. We can change hertz RPM. That didn't work. So that's the basic overview of that particular setup. We've got this fine max here, which should bring up the spectrum and move the cursor to the maximum amplitude. For whatever reason that's occurring, it thinks it's occurring out in here. Pretty useful in the real set of data. You click that and just boom, it just puts it in the waveform, moves it where our the spectrum with the maximum amplitude is, and so forth. So it's waveform subset. We can make this smaller, or we can simply type in a number. Let's say we want to go from 20 seconds to 28 seconds or 30 seconds. Hit a 3 there. Once again, you can see our taps on the accelerometer with our finger while we acquire the data. One more option, our waterfall plot. And what we got here is basic defaults. Got 200 plots. Our resolution is 16,000. Seems to be a pretty good number. This number we can change back to say 0.2, and it will increase the amplitude of our data. And if you notice, we've got a little red arrow here. If I click part way up through here, it will bring that cursor and it will overlay the data that's actually at that point. Note also that I've got a vertical cursor that I can move over if it will come up. There we go. And it shows me kind of the same frequency across the spectrum. So a little bit of cursor capability here on our waterfall spectrum. So that's basically the use of the different plots. If we were to go choose one of these other ones, the spectrum updates, notice that it went back to here. I'll make this a smaller number, and it pulls that up, just shows the electrical noise in the circuits. Notice got a 2000 or 200 hertz at max. Once again, I can change that by say typing in 1,000 here. So we had data that was good to 1,000. Notice that it pushes everything down to the lower frequencies here. Notice that we still have our individual spectrums and the individual cursor that goes through that. So we move that down just by clicking on the scale. We can single click on the scale, moves both of these guys around to try and hit that or highlight that spot where the cursor or where you clicked. So just a way to kind of look at some individual data and have it highlighted and show up for you. So that's the basic functioning of the software. Most of the analysis is done from this particular point, and of course we can set this back to 0, out to 100 on this end if we want, and there we are back to our initial setup, and pull our cursor around here where we want it to show the data from. Note that we can do that. And that concludes our